IP core considerations for ensuring functional safety in safety-critical applications. I would like to quickly introduce myself. My name is Philipp Jacobsohn. As a member of SmartDV's applications engineering team, I'm responsible for various tasks, mainly ensuring that our products can be used without much guesswork. In addition to technical support, this also includes connecting our customers to relevant contacts in our R&D department. With several hundred development engineers responsible for the implementation of hundreds of different IP cores, this is not always an easy undertaking. I hope that in today's presentation I can shed some light on the benefits of using predefined circuit functions, so-called IP cores, in safety-critical applications, and also provide some guidance how to do this. In fact, successful adoption of such IP cores primarily means foresight and serious planning. Unfortunately, it is often forgotten that it is extremely important to get the manufacturer of complex functions on board at an early stage of a project. On the other hand, if close collaboration with third parties is not considered, this can lead to misunderstandings, time pressure, delays, and mutual frustration. Of course, you want to avoid all of this in a project. But now, let's get started. Let's start with an important topic. What are safety standards? Today's presentation is all about ensuring security through standardization and IP selection for safety-critical chip designs. First, let's take a quick look at the different industry standards available. The common standard in the automotive sector is ISO 26262, which is a subgroup of the IEC 61508 standard. On the other hand, DO 254, which is actually the design assurance guidance for airborne electronic hardware, and AMC 20-152A, which is basically an addition to DO 254, are the common standards that provide requirements for engineers developing airborne electronic hardware. As a next step, I would like to discuss the question of why standardization is needed in the context of circuit development. To be clear, the topic discussed today is not something that can be considered new or even exciting. Safety standards are often even viewed as necessary evil, and yet it is a case that the operation of electronic circuits is no longer possible without clearly defined rules of reliability and operational safety. Similar to a pilot who has to work through a protocol with all safety-related procedures before taking off the aircraft, this also has to happen as part of circuit development. Even if the pilot has already gone through the same process hundreds of times and successfully completed a corresponding number of flights, this procedure must be carried out again before each new flight. The only goal of this measure is to avoid errors, and that is exactly what is provided by predefined standards, for example ISO 26262 or IEC 61508. A firmly defined structure that allows possible errors to be discovered, problems to be classified, and thus to be able to react adequately and reproducibly to the occurrence of unforeseen situations. If a tire is damaged, the aircraft must be prevented from taking off. However, if the onboard kitchen is defective, this might be acceptable. So why different standards? Also, the goal of a ship captain and the airplane pilot, for example, are identical, namely to bring the passengers safely to their destination. Different criteria are relevant for this task. And it is precisely for this reason that different standards have been defined for different tasks. However, the supplier of the respective means of transport must know in advance whether, for example, the gyro compass is to be installed in an airplane or cruise ship. And that's why an IP vendor needs to know the environment in which its predefined function is to be used. Now let's go ahead with the next important question. What do safety standards define? First of all, the individual phases of the project implementation are defined. This procedure is more or less uniform for all standards. These are the following steps: planning, implementation, verification, and documentation. However, it should be noted that each standard defines the applicable requirements for planning, implementation, verification, and documentation slightly different. The tenets of all these steps must be met for the standard to be satisfied. Potential hardware failures must be categorized in order to define appropriate mechanisms for error handling. For example, an error in a car infotainment system might be acceptable, while an error that affects safety gear, such as automated braking system, is not. Therefore, the IEC 61508 standard, for example, is subdivided into 5 safety integrity levels, SIL 0 to SIL 4. The ISO 26262 standard comprises 4 levels, ASIL A to ASIL D, where ASIL stands for automotive safety integrity level. The higher the category level is, the stricter the safety requirements, with SIL 4 or ASIL D being the most stringent.
A product's end use plays a vital role in determining the approach that must be taken in design and verification. A chip that makes its way into an automotive infotainment system, for example, would cause a nuisance to the driver if it were to fail, but it would not present any risk to human life. By contrast, the malfunction of a chip in an airbag or lane management system could threaten the safety of a driver, their passengers, or other vehicles on the road, even pedestrians. When a chip design's end use could mean that human life hangs in balance, we refer to these designs as safety critical. Functional safety is essential in such designs. Thus, the integrity level of such designs must be commensurate with end use. Potential failures caused by software or hardware must be planned for and proactively addressed.
Let's also take a closer look at understanding and reacting to potential malfunctions. Fundamentally, it is all about the definition of how a system can address a failure case and determine either how to prevent the failure itself or how to react on it. A distinction must be made here between hardware and software errors, which can be either safely ignored or must be prevented or reacted to with different approaches in each case. But even with pure hardware errors, it is essential to understand what malfunctions can actually result from these and what an appropriate reaction should look like. A distinction is made between systematic errors, which result, for example, from errors in circuit development or insufficient verification, and randomly occurring errors, which are caused by external influences. It is important to understand that systematic mistakes cannot be avoided in every case. It is possible to greatly increase probability of providing an error-free product through good verification coverage, standardized test procedures, and extensive testing, possibly also supported by using dedicated verification IP, and of course also by using through specialized tools. Nevertheless, it is a case that 100% coverage can hardly be achieved, and the corresponding standards also explicitly emphasize this. Now, how is IP development impacted? Or to put it in another way, when creating or using IP for safety critical designs, what does an engineer need to bear in mind? Even if only a certification of the final product is to be carried out, each component must meet the requirements that apply to the overall system. Therefore, it is necessary for all subcomponents to carry out the circuit implementation in compliance with strict rules and to take into account the subsequent use of the product in safety-related applications. And this has to be done, of course, already during the development phase. The previously mentioned standards define processes that must be maintained. In case of the ISO 26262 standard, there are detailed planning during which the requirements for functional safety are defined, and analysis intended to identify hazards and possibly error modes. The implementation phase taking into account the two previous steps. Subsequently, verification and validation of the system takes place. To achieve certification, all sub-steps must be well documented and the results recorded, including the tools used, verification methods, and so on. It takes some substantial effort to achieve this type of certification. Additional tasks are necessary to create appropriate documentation. This means verification process, error coverage, error reports, tool usage, and so on. It should also be noted that only a certain frozen version of a product is qualified, which remains unchanged after receiving the certification. Also, tool versions that were used when creating the product must remain the same. To ensure compliance with the safety standards, such as IEC 61508, it is necessary to obtain certification. Companies must work with an independent organization, such as TÜV Süd in Germany, So there are many such bodies around the world, to complete the certification process. To achieve certification according to DO 254, it is mandatory to firstly use clear definitions and terminology during the specification phase to ensure full traceability from the start, to specify precise requirements, and to ensure meticulous documentation. On the negative side, the entire process up to obtaining a certification is time-consuming and requires appropriately trained personnel. It is also necessary to carry out audits with the certifying organization during the entire period of certification, during which the completeness of the measures for achieving functional safety are checked and proven. On the positive side, certification can increase customer confidence that a product has the quality and reliability that they are looking for. In most cases, it makes no sense to certify individual subcomponents such as IP cores, as these are used in the context of a more complex circuit anyway. But it is necessary for all subcomponents to comply with the strict rules specified by appropriate standards and to take into account the subsequent use of the product in safety-relevant applications. As mentioned before, even if only a certification of the final product is to be carried out, each component, including third-party IP cores, must meet the requirements that apply to the overall system. Therefore, it is necessary for all subcomponents to carry out the circuit implementation in compliance with strict rules and to take into account the subsequent use of the product. Now, a note not only in our own interest. How can SmartDV help you? SmartDV has verification IP that is created by verification engineers with decades of experience in verifying complex chips. SmartDV also offers standard-based design IP for a variety of applications. We are ready to be your trusted partner in automotive and avionics designs. Shown is here a selection of applicable IP for these types of chips. The process of verification is growing more intricate with each passing year as the complexity of chips continues to increase. In turn, verification tends to consume about 60 to 80% of project resources and often represents a bottleneck. Having all this in mind, it pays to work with a trusted partner who can help you to achieve your chip design goals. Whether you are sourcing design IP for your next SoC, ASIC or FPGA project, or seeking verification solutions to put your chip design through its paces, we can quickly and reliably customize our extensive portfolio to meet your unique needs. Our smart compiler technology makes it easy to get IP your way. Simply define your specs and let us handle it from there. Thanks a lot for listening to the presentation, and please make sure to visit us at our exhibition table. Thank you.